Hi everyone, this is the first video in this unit where we talk about titrations. After I've given an introduction and talked about the fundamentals, we'll have time to do 3 problems. The setup for a well, first I have to be able to say it. The setup for a titration is you have typically an Erlenmeyer flask, some aqueous sample, and in this case we're going to put acid. Let's say we're titrating a sample of acid rain, and we know the volume. Let's make it 28.0 milliliters of acid rain, but we don't know its concentration. Question mark, concentration. Now, acid rain, what happens is different gases, one of them being nitrogen dioxide, mixes with rain or mixes with water in the clouds, and it forms actually nitric acid, HNO3, a strong acid, plus NO. And then the balancing is what? Oh, I should have done this before. Oh, how about this? 2 NO, NO2. 1, 2, 3. Oh, okay, 2 there, and then 3 NO2. Okay, is that balanced? 3 NO2. You have 2 hydrogens, 3 nitrogens, and 1, 2, 3, 6, 7. 1, 2, 3, 4, 5, 6, 7, 7 oxygens. Okay. We need to figure out the concentration of that acid rain, and we're going to think of it as nitric acid. What you have here is a burette filled with base. And you you want to make sure that you line up the Erlenmeyer flask with the burette, and the burette has base in it. That base you will make in the lab, so you have a very good idea what the concentration is. And let's say this is 0.5000, okay, 4 significant figures of NaOH. What happens is you're going to put an indicator, because right now those 2 solutions are most likely colorless, and an indicator will change color. So for instance, the indicator phenolphthalein. It's colorless under acidic conditions, and it turns pink under basic. So when the solution is acidic, it's colorless, and it should be colorless now if we think that the rainwater is acidic. And then as you're titrating base, if it's basic, it's now going to have a slight pink color. Pink. And you want to catch it at that point and figure out the volume. So basically, what you're figuring out is what volume do you need to get this to turn faint pink, just at the border of acidic and basic. Okay, so we need to figure out what volume. Now, I threw out a couple words that are new to us. This is the titrant, Titrant, and the verbiage is we are going to titrate acid rain with 0.5000 molar of base, and the base is NaOH aqueous. Okay. Now, there's one more definition, and it has to deal with what equivalence is. And I want to be very careful with this definition. It's not when the H3O plus concentration is identical to the OH minus concentration. Although in some titrations it is that, but not always. So the equivalence point is when, it's a very subtle definition, but it's when the concentration of the titrant in the flask, as you add it, when the concentration of the titrant is equal to the concentration of the solution in the flask. Okay. Honestly, I'm not too enthusiastic about that definition. Let me give you, that's true, but you may get in trouble if you try to apply this directly to a diprotic acid. So let me say it this way. It's, how about this? This is a better definition. When enough titrant, and in this case it's the base, when enough base is added to, the keyword is neutralize, to neutralize the solution in the flask, and now in the flask, that's where your acid is. Okay, let's keep that in mind. So there's the setup. You are adding titrant, or you're doing a titration until you get to the point where you're at the acidic basic border, and that border is the equivalence point because that indicates when enough titrant, I don't like this first one, let's use this one, when enough titrant is added to neutralize the solution in the flask. Now, you could have it reverse. You could be titrating a base with a titrant that is acid, but this is the most common setup. Okay. Look at the problems that we're about to do and what could be asked. Now that we have a decent idea of the equivalence point. Problem number 1. Let's compare and contrast these 3 problems. Problem number 1. What is the concentration of HNO3 if it takes 27 milliliters of 0.400 molar NaOH to reach the equivalence point? So the question is, what is the concentration of acid? This is question mark. When we get to that point in the titration where we reached equivalence. Okay. We know this is a strong acid. And NaOH is a strong base. I'll tell you now, any calculations with the equivalence point, I should rephrase that. Any calculations concerning the equivalence of volume, right? We have the equivalence point, but from that point we can figure out how much volume of titrant was used. Okay. It doesn't matter how to calculate for the equivalence volume if you have strong acid or strong base, or weak acid or weak base. And I'll show that in these examples. Look at the problem number 2. Ask for something different. What is the volume of titrant? Okay, so now how much base do I need if I know the concentration and the amount of what's in the flask? So this is like a prediction. So this is predict the amount of base. And this is really, problem number one is calculate the concentration of acid. Calculate concentration of acid. And again, we are going up to the equivalence point. What's going on here? There's something slightly different. We have still the strong base. Okay, that's perfectly fine. But we have a diprotic acid. Diprotic. And that is going to change the calculations a little bit. We have to account for that. Because we are using a strong base, we will deprotonate sulfuric acid twice, okay, to get rid of both protons. So here is predict the amount of base, and we're using a diprotic acid. Okay. Problem number 3 is very, very, very similar. We still want the volume of titrant. We still have a strong base. Oh, by the way, you know that H2SO4 is a strong acid. But look at this. HF is a weak acid. I'm telling you now that it doesn't matter. So this problem 3, it doesn't matter if strong or weak acid when calculating the equivalence of volume. That's important. It does matter, we'll see, it does matter when we calculate the pH. But if you're just calculating the equivalence of volume, it doesn't matter. It doesn't matter if strong or weak acid for equivalence volume. Okay, it's just practice because we're doing for problem 3 the same exact thing as we're doing for problem 2. Okay, let us tackle these. At the equivalence point, we need enough base to neutralize all of the acid. In this question, they're asking what is the concentration of HNO3 if we use this much base. So we're going to take the amount of base and figure out how many moles of OH was created. Because we know that it's the OH minus that neutralizes the H plus of nitric acid. And if we could set those equal to each other, we have reached equivalence point. So in this case, yes, the OH minus concentration will equal the H plus concentration. They're both strong. Okay, so they're both fully dissociated. I am going to go ahead and convert it to liters. 0.0279 liters of, let's put our compound. Let me make sure this is focus also. Okay. Times. We have a molarity, so we'll have moles on top because we can cancel out liters on the bottom. And now here's the trick. We know that we need 1 mole of NaOH to neutralize 1 mole of HNO3. 1 mole of NaOH to neutralize 1 mole of HNO3. At this point, okay, good. At this point, we have the moles of HNO3, right? See, we want the concentration. So now we just need liters. What is the concentration of HNO3 if it takes 27.9? Oh my goodness. I've never told you how much HNO3 we have. That is a huge mistake. Um, right? Because we would know the amount of the acid in the flask. So let me put here 50.0 milliliters. My bad. Because we now have moles, and we need moles per liter. So now this is, we're going to put liters on the bottom. 0.050 liters. Okay, let me prove to you that the units cancel out properly to give us concentration, molarity. Liters go away. NaOH goes away. Moles goes away. And then we have moles of HNO3 in liters. And that's a molarity. We were able, once I gave you the volume of the solution in the flask, we're able to get on one line the answer. 0.0279 times 0.0400 equals times 1, then divided by 0.050 liters, I get 0.022 molar of HNO3. Okay. That is for problem number 1. Problem number 2 is different because instead of asking for the concentration, I gave you the concentration of everything. I want us to predict how much base we need. How much base we need to get to equivalence. And don't worry about that this is diprotic just yet. We'll take care of it where? We'll take care of it when we do this portion of the dimensional analysis. Alright, so what do we know? We can definitely know the moles of H2SO4. Okay. So here we have 0.010 liters of H2SO4 times the molarity, 0.1000 moles per liter. Okay, that's the concentration of H2SO4. So there's a couple of conversions we need to add. We got to get, how should I say this? Actually, no. There's only one conversion where we cross over the mole bridge, and this is going to be, you need 2 moles of NaOH to neutralize 1 mole of H2SO4. Okay, does that make sense? Your acid is diprotic. You need twice as much of this NaOH base. Now, if the base was, for instance, I don't know, CaOH2, and you have 2 hydroxides, then it would be a 1-to-1 ratio. So that's where we use the 2 to account for that we need double the amount of base to neutralize the amount of acid. So now we have moles of base. We want volume. So we need liters on top and moles on the bottom because we are given the molarity. So here we have 0.0250 moles per 1 liter. This will give me the volume in liters. Okay. So again, in one line, I think we're able to get the answer. 0.010 times 0.1 times 2, then divided by 0.0250. Okay, so I got 0.080 liters, and that's equal to 80 exact 0.0 milliliters of what? Of NaOH. Okay, very interesting. And that makes sense. It's 80. We started out with 10 of the diprotic. The diprotic acid is like 4 times more concentrated, but also it's diprotic, so you would imagine 8 times. If you do that in your head just by inspection. All right, I'm telling you, don't worry that it's a weak acid. You're going to do the same calculations to get volume of NaOH that we did up here. Okay, it's because even if it's weak, that is such a strong base that it's going to deprotonate even a weak acid. And to get to equivalence, the equivalence is what? To neutralize all of the acid, regardless if it's strong or weak. Okay. Number 3, same calculations. We have the moles of acid, or we're going to calculate the moles of acid. So here we have, again, 10 milliliters of HF, and then its molarity is 0.0550 moles per liter. And then, again, we are neutralizing all of that acid. So it doesn't matter if it's weak. That's a strong base, it will do it. It will neutralize that weak acid. Times, now the molarity of, and actually I used KOH. The molarity of KOH is, yes, KOH. The molarity of KOH is 0.0690. Okay. But we want liters on top and moles on the bottom. 0.06901. Okay, let's do those calculations. 0.01 times 0.0550 times, oh no, not times, equals, so we're up to here, divided by 0.0690, interesting, 0.0080, it's really 797, but we round, that's liters, and so that equals 8.0. That is, again, coincidence. I'm not sure. I picked these numbers randomly, so I'm not sure how it turned out to be that way. 8.0 milliliters. Now, let's take a look at here. Okay, yeah. So we have 10 milliliters of this concentration. The base is a little more concentrated, so it takes a little less base than 10 milliliters to neutralize the HF. I am a little bit freaked out because, again, I made up these numbers 30 minutes ago, and we get 80 and 8. Double check my work, make sure that these are correct, and that is a couple problems where we work with the equivalence point and work with the equivalence volume, either using the amount of base to figure out the concentration of acid, which is problem number 1, and problem number 2 is to predict how much base would we need if we had this much acid. All right, the next couple of videos we're going to go look at some graphs of different types of titrations and calculate a bunch of the stuff, equivalence volume, and also we're going to look at calculations for pH.